Hello everyone. In this part of the lecture on sequential circuit analysis, we are going to analyze another example. We have the logic diagram given to us. There are three flip-flops, D-type flip-flops, which are sensitive to the rising edge of the clock, and their outputs are called as A, B, and C. So A, B, and C here are our state variables. A, B, and C. We have a single output, which is Z. Output is Z, and there is no input. So what we need to specify here is the expressions for the output, Z of t, and also for the next state. So here we will have the expression for A at t plus 1. Here we will have it for B at t plus 1. And here we will have it for C at t plus 1. Okay? And you know that we can determine the expression for them by referring to the schematic here, to the circuit schematic here for A, B, and C at t plus 1, and then obtain the expressions for all of them. So let's do it for Z first. We can see that Z is easily determined as Z of t is equal to A at t. So that's quite straightforward because it's directly connected to the output of the first flip-flop. Then for A, B, and C at t plus 1, we need to find out the expression here. For A at t plus 1, I'm going to write it here. We have AND of two values, the first one and the second one here. If we follow them, we can see that the first one is here and it is connected to B. So A at t plus 1 will be equal to B at t, and the second input to the AND is coming from C. So A at t plus 1 is equal to B and C at t. Then for B at t plus 1, we have OR of two values. So we'll have OR of two values, and both of them are the output of the AND functions, AND gates, and the input to those ANDs are coming here. So the first AND here has the input as C, and the output of the inverter is not B. So I will write it here. C and not B. And for the second one, we have B and not C. So B at t plus 1 is equal to B and not C, or not B and C. So basically we have the XOR expression here. For B we have B and not C, or not B and C. And finally for C at t plus 1 we have the not C here, and the second input to the AND comes from the A. So here we have A, therefore not A. So not A, not C. For C at t plus 1, we have not A and not C. Not A and not C. And in this way, we have obtained all the equations or the expressions for the output and also for the next states. And now we can fill the state table. We have A, B, and C as the state variables. There is no input, and not A at t plus 1, B at t plus 1, and C at t plus 1 are the next states. So basically this means here A at t plus 1. And we have the output. How can we fill this state table? By referring to the equations that we have here. For Z, it's quite straightforward because Z is equal to A Therefore, for Z, we'll have 0, 0, 0, 0, 1, 1, 1, 1. Then for A, B, and C, we need to refer to the expressions. For A, we have B and C. So A at t plus 1 is equal to B and C at t. So basically A will be equal to 0 unless both B and C are equal to 1. And that's when we have this row or this row. And other than that, A at t plus 1 will be equal to 0. Then for B, we have not B and C or B and not C. So B will be equal to 1 only when one of the B and C is equal to 1. So the next state of the next value of B, of course, B at t plus 1. Otherwise, it will be equal to 0. So we will have 0, 1, 1, 0, 0, 1, 1, 0. And finally, for C, we have not A, not C. C at t plus 1 is equal to not A and not C. When both A and C are equal to 0, C will be equal to 1. Otherwise, it will be equal to 0. So here we have 1, 1. And then for the rest, it will be equal to 0. So in this way, we have filled the state table for this example. And now the next step will be to obtain the state diagram. In order to obtain the state diagram, we can check, first of all, the number of the states that we have. We have 3 state variables. So we have 8 states here. For each state, we will use a circle. We can use the numbers here 0, 0, 0, or we can also use their equivalent decimal number like 0, 1, 2, 3, 4, 5, 6, and 7. So both of them are fine. Or we can alternatively use any name for the states that you desire. Here we can use just 0, 0, 0, and then 0, 0, 1, and so on and so forth. So if we look at the first row, we can see that if we are in state 0, 0, 0, the output is equal to 0, and the next state is 0, 0, 1. 0, 0, 1. We have the transition, and there is no input. When we are in 0, 0, 1, the output is equal to 0, and the next state is 0, 1, 0. 0, 1, 0 is the next state. And when we are in 0, 1, 0, the next state is 0, 1, 1, and the output is 0. Let me draw it here, 0, 1, 1. When we are in 0, 1, 1, the next state is 1, 0, 0, the output is 0. So from 0, 1, 1, we go to 1, 0, 0. When we are in 1, 0, 0, the next state is 0, 0, 0. The output is 1. And we have 3 more states to consider. 1, 0, 0. If we are in 1, 0, 1, 0, 1, the output is equal to 1. And the next state is 0, 1, 0. And you can see that it is here. Then if we are in 1, 1, 0, 1, 1, 0, the output will be equal to 1, and the next state is 0, 1, 0. So again here. And finally, if we are in state 1, 1, 1, the output is equal to 1, and the next state is 1, 0, 0. So 1, 0, 0 will be the next state. And we have no inputs in this case. You can have a look at the state diagram here. It's indeed the same state diagram, but shown in a different way. You can see that if we start at 1, 0, 1, 1, 1, 0, and 1, 1, 1, we will transit to another state which is inside this loop. And we'll never go back to any of these states. But if we start at any state here and at the reset at the beginning we start with 0, 0, 0, we will always remain inside this loop. So the 3 states that are shown here will not be used. Okay. So basically we will start from 0, 1, 2, 3, 4, and 0. So basically it will be kind of counting from 0 to 4 and then going back to 0. If for any reason we start at 5, 6, or 7, we will go back into the main loop and the counting will continue inside the loop indeed. Okay, so now let's go through another example. Here we have a sequential circuit with 2 D-type flip-flops, A and B. There are 2 inputs, X and Y, and we have 1 output, Z. And the circuit is specified by the following input equations. A at t plus 1, B at t plus 1, and Z are given. We need to draw the logic diagram of the circuit, derive the state table, and derive the state diagram. We already know that there are 2 D-type flip-flops, so we can start drawing them first. They are going to receive the clock, and their clock will be connected to each other and to the main clock of the system. They are D-type, so the input to them will come from the data input. We will have Q and not Q. The output of the first one will be considered as A, and for the second one will be considered as B, and we also have the Z, the output. To draw the logic diagram of the circuit, we just refer to the expressions that we have here, A at t plus 1, and determine the input to the corresponding flip-flop. So for the first one, we need to have not X and A or X and Y. So we need to have an OR gate here, which receives 2 inputs, and both of them are coming from AND gates with 2 inputs each one. And now we need to connect them properly. For the first AND gate, we will connect it to not X. If I assume that we have access to the X, we need to use an inverter, not X, and A. And for the second one, we have X and Y. For the second one, we will connect this to the first input X and the second input Y, because we have 2 inputs. So in this way, we have done it for the first flip-flop's input. For the second flip-flop, for the input of the second flip-flop indeed, we need to construct the equation given here. Again, we need to use an OR gate, which receives input from 2 AND gates, and those 2 AND gates have 2 inputs, X and A, or not X and B. So X and A means that we need to connect this here X and A. We have it here. So this dots means that we have a connection here. For the second one, we have not X and B. Let's use another color maybe here. Not X and B. And finally for Z, we have X and B. Therefore, we need to have an AND gate, which is connected to B and X. Which is here as well. Okay, so we have the logic diagram of the circuit drawn here. As the next step, we need to derive the state table. In order to derive the state table, we need to look at the state variables A and B, and we also have 2 inputs, x and y, we can consider it in this way. So we have 4 indeed inputs in total, and we have a at t plus 1, b at t plus 1, and z as the outputs. So basically, in this case, the state table that we have will include 16 rows. Alternatively, we could take x and y into the output side. Both are fine, but let's keep here this way. So to derive the state table, we would need to fill the input side with 0, 0, 0, 0 up to 1, 1, 1. So I'll do it quickly. And then we have it for okay, so we have the input side filled. For the output side, a at t plus 1, b at t plus 1, and z, we just need to refer to the expressions that we have here. For example, for z, we have x and b. For z, we have x and b. It means that whenever both x and b are equal to 1, z will be equal to 1, which is this case here, and the case here. And apart from that, z will be equal to 0 all the time. I hope the number of zeros that I put here is correct, but anyways, we have these two ones here and the rest will be equal to 0. And for a and b at t plus 1, we also refer to the expressions here and we fill the state table, and it will look like this, as you can see here. Okay, so I don't go through the details again. If you look at this as a truth table, here we have the inputs and here we have the outputs. And a final step here, is to construct the state diagram. As we have two state variables, there will be 4 states. So for a and b, we have 4 possible values in terms of combination of their values. We will have S0, S1, S2, and S3, as you can see here. S2 and S3. S0 will represent 0, 0, S1, 0, 1, S2, 1, 0, and S3, 1, 1. And these are the values that we have for A and B. And then we refer to the truth table here and determine that if we are in state 0, 0, if we receive 0, 0 as the input, the next state will be 0, 0, and the output will be equal to 0. So we will remain in 0, 0 if we receive 0, 0 as the input, and the output will be equal to 0. And then in the next row, we are in state 0, 0. We receive 0, 1 as the input. We still remain at the same state. The output is equal to 0. Similarly, for the third row, if we receive 1, 0, we'll have 0, 0 as the next state. We remain at the same place, and the output is equal to 0. So basically, if you consider these 4 lines together, you can see that in all cases, the output is always equal to 0. So for S0, we can already write that the output is equal to 0. And then for 3 cases, for the first 3 rows, we will remain at the same state, and we can possibly combine them with each other indeed. But only for the 1, 1 case, for the input, we will switch to the next state, which is 1, 0. And that's indeed state number 2. So with input equal to 1, 1, we will switch to S2. Otherwise, we will remain here. And those 3 cases are here. So with 0, 0, 0, 1, and 1, 0. 0, 0, 0, 1, and 1, 0 will remain in the same state. And I guess you can see it here as well. So we are in S0. if we receive 1, 1 as the input, we will switch to the S2, the output is equal to 0, and we will remain at the same state if we receive 0x, which means that we have 0, 0, 0, 1, or we receive x0, which means that we have 0, 0, or 1, 0. So this means that if we receive 0, 0, 0, 1, or 1, 0, we will remain at the same state and the output is equal to 0. And you can do it for the next states as well. For example, if we are in 0, 1, let me draw it again here. If we are in state 1, 0, 1, first of all, you can see that the output doesn't depend only on the state. Therefore, it will depend on the input as well. If we are in S01 and we receive the input either as 00 or 01, we will remain at the same state. Okay, so these two could be combined with each other. So we will remain at the same state if we receive the input as 00 or 01. So 0x could be written here. This includes 00 and 01. But if we receive 10 as the input, if we receive 10 as the input, the next state will be 00. So we will switch back to 00, S0. If we receive 10 as the input, and in this case the output will be equal to 1. In the previous case the output was equal to 0. And finally, if we receive 1 as the input, the next state will be 10. So 1 as the input, the next state is equal to 10, and the output will be equal to 1. Let's have a look at the next 4 rows. If we are in state 1, 0, which is S2 here, you can see that the output is equal to 0 all the time, so we can show it here. For the first two inputs, we will remain at the same state, 1, 0. So for the combination of 0, 0 and 0, 1, so for 0x, we will remain at the same state, S2. If we receive 1, 0 as the input, we will switch to the 0, 1. If we receive 1, 0 as the input, and if we receive 1, 1 as the input, we will switch to 1, 1. So 1, 1 will be S3 here. And finally, if you look at the last 4 rows, when we are in state 1, 1, for the first 2 rows, 0, 0 and 0, 1 as the input, we will remain at the same state. For 0x, we will remain at the same state and the output is equal to 0. If we receive 1, 0 as the input, we will switch to 0, 1. So 1, 0 as the input, the output will be equal to 1. And if we receive 1, 1 as the input, the next state will be 1, 1 again, and the output will be equal to 1. So we will have this as well. If we receive 1, 1 as the input, the output will be equal to 1. And therefore, our state diagram is complete. And you can double check it here as well. So basically, this is identical to the one that I just drew. Alright, so I think that's the end of this video lecture. I hope you have enjoyed watching it and you have learned how you can analyze the sequential circuits by constructing the state table, by finding out the expressions for the input, for the outputs, and also for the next states, and by drawing the state diagram and filling it. Thank you for watching and see you in the next lecture later. Bye for now.